Alright, in this video we're going to start section 7-3, and we're still looking at volume, but we have a new method as opposed to the disk or washer methods. Now we have the shell method. So in this section we're going to find the volume of a solid of revolution using this new shell method and compare the uses of the disk method and the shell method. Sometimes one is preferable to the other. It's much easier maybe to use the shell method as opposed to the disk. And there are going to be some functions, depending on what the function is and the axis of rotation, where it might be impossible to use one of the methods, so we're forced to use the one that is available to us. So the shell method. In this section you're going to study an alt method for finding the volume of a solid of revolution, and it's called the shell method because it uses cylindrical shells. A comparison of the advantages of the disk and shell methods will be given later in this section. To begin, consider a representative rectangle as shown in the figure below, where W is the width of the rectangle, H is the height of the rectangle, and P is the distance between the axis of revolution and the center of the rectangle. So down here in our photo, or our picture, we see that our axis of rotation is horizontal. It's the x-axis. And usually with the disk method and the washer method, our representative rectangle was perpendicular to and sometimes touching our axis of rotation. In the shell method, it will not be perpendicular to, it will be parallel to. So here is our representative rectangle, and we're going to take that representative rectangle and spin it around our axis of revolution. So we are going to create a shell of thickness W, that's the thickness of our representative rectangle, and it will be hollow. So let's see here. When this rectangle is revolved about the axis of revolution, it forms a cylindrical shell or tube of thickness W. To find the volume of the shell, consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell, and the radius of the smaller cylinder corresponds to the inner radius. Because P is the average radius of the shell, you know the outer radius will be P plus half W, and the inner radius will be P minus a half W. So there we have an outer and an inner radius. Again, P is just the distance between our axis of revolution and the center of our representative rectangle. Remember, the representative rectangle's width is W. So we look at the inner radius, or P minus half of that distance, half of W, and the outer radius, P plus that half of W. So to find the volume of the shell is going to be the volume of the cylinder minus the volume of the hole in the middle. The outer volume, or the volume of the outer radius, the volume of that cylinder is going to be P plus that half of W, quantity squared, times pi times h. And then we'll subtract the inner radius, or the volume of the hole. And if we FOIL out those binomials and we distribute the negative and we collect all our like terms, it all boils down nicely to this. 2 times pi times p times h times w, where p is the average radius, h is the height of the rectangle, and w is the thickness of the shell. So let's think back to the disk method. For disk method, or the washer method, the volume was equal to pi, and then we had our integral, and we had capital R of x squared, that was our outer radius, minus lowercase r of x, quantity squared, and since we were integrating with respect to x, dx. And we could do the same thing for y, but it would be r of y quantity squared minus r of y quantity squared dy. Let's compare this formula that we know and love with what we are looking at here, these new shell method formulas. Let's start here on the right with integrating with respect to x. So we're rotating around the y-axis. We are not perpendicular to the axis of rotation, now we are parallel to it. So our width is delta x, so we're going to be integrating with respect to x, hence the dx. The dx up here. P of x, the first part of the formula, well, let's look at the whole thing first. Volume equals 2 pi, integrated from a to b, of P of x times h of x dx. So what is P of x? P of x is just the distance we are away from the axis of rotation. You know, here is going to be our x-axis, so most of the time P of x is just going to be x. H of x h of x is the height of the rectangle, and the height of the rectangle is dictated by the function that we are finding the area under, and then we'll eventually spin that around and turn it into a volume. So h of x is given by the height of the function. If we look at a x-axis of rotation, horizontal axis of rotation, here we're rotating around a horizontal axis, or the x-axis, and the integral is 2 pi integrated from c to d of p of y h of y dy. P of y is still the distance between our rectangle and the axis of rotation. So here, most of the time, p of y is going to be the y variable. H of y is the height of the rectangle, dictated again by the function h of y, and then we integrate with respect to y. So let's try one out here. Example 1. Find the volume of the solid of revolution formed by revolving the region bounded by this function, y equals x minus x to the third, bounded by the function and the x-axis between 0 and 1, and we're going to rotate about the y-axis. So here's our pretty little picture. Our axis of rotation is y. We are parallel to it, and since we're perpendicular to the x-axis, we'll be integrating with respect to x. So our volume is going to be equal to 2 pi. We're going to integrate from a to b, and our function is p of x h of x dx. So that's our generic formula from the previous slide. Let's plug in the information relevant to our problem. So the volume is going to be 2 pi, and we're going to integrate. We're integrating on the x-axis. We are perpendicular with our representative rectangle to the x-axis. So we will be integrating from 0 to 1. Lower limit 0, upper limit 1. Next we need p of x. P of x is the distance between the axis of rotation and our representative rectangle. Well, here's our axis of rotation. Here's just an arbitrary representative rectangle. The distance between the y-axis and this rectangle is simply the x-coordinate. So p of x is just x. And we're going to multiply that by h of x, which is the height of the rectangle. And here, what dictates the height of our rectangle is our curve. And the formula for our curve is x minus x to the third power. So the integral is set up. We're not quite ready to integrate yet, but we're really close. So let's distribute that x throughout the parenthesis. So 2 pi integrated from 0 to 1. And now we distribute that x. X times x is x squared. X times x to the third is x to the fourth dx. So the integral is not going to be outrageously hard. Just two terms there we have to integrate. And out front we still have our 2 pi. And now we take the antiderivative. The antiderivative of x squared is x to the third over 3. Minus x to the fourth becomes x to the fifth over 5, and we evaluate from 0 to 1. So we start by plugging in our upper limit of integration, drop in the 1, and we get 1/3 minus 1/5. And for completeness sake, we're going to minus the lower limit integrated or evaluated, even though we're just plugging in zeros. 0 to the third is 0 over 3, and 0. 0 to the fifth is 0, divided by 5 is 0. So, you know, for completeness I put it there, but that's not going to affect the problem at all. So, let's work in there on our fractions. Outside we have 2 pi. And if we work inside and get a common denominator between 3 and 5 is 15, and then multiply up. 5 minus 3. So we have 2 pi times 2/15. And we multiply straight across, and we get 4 pi over 15, and that would be units cubed. We are looking at a volume here, so that would be some kind of cubic units. Alright, let's take a peek here then at example 2. Now our axis of rotation is the x-axis. So our representative rectangles will be parallel to the x-axis. Find the volume of the solid of revolution formed by revolving the region bounded by the graph of, and here's our function, x equals e to the negative y squared power. We're bounded by that graph and the y-axis between 0 and 1. We will rotate about the x-axis. So our generic formula is volume equals 2 pi, definite integral, and we have p of x, or p of y, excuse me, p of y, h of y, dy. And let's plug in our problem's numbers. We're integrating from, or 2 pi. Our integral will go from, we're integrating with respect to y, so we're walking up and down the y-axis, and we're walking from 0 to 1. Our definite integral is from 0 to 1. P of y. What is the distance between our rectangle and the axis of revolution? And because our axis of revolution is the x-axis, the distance from our x-axis to our rectangle is simply our y-coordinate. And let me slide this over a little bit here, and you'll see why in a minute. Next, we need h of y. H of y is how high is our rectangle. Here it is. And the height of the rectangle is dictated by the curve. And our curve is e to the negative y squared. So looks like we're ready to integrate. So let's see here. Looks like we're going to have to do a u substitution. We have a composite function. We have e raised to a power, and that power is not simply x, it's something more. It's a function of its own. So to do a u substitution, ooh, and I forgot my dy, I'm going to change this to e to the u power. And that means we're going to let u equal negative y squared. I don't like the look of that too. There we go. So what is the derivative of u? Well, du with respect to y will be du dy equals negative 2 y to the first, and then I would multiply both sides by dy. So our du is negative 2y dy. Let's see if we have that in our setup. Well, we have y dy, so what we're missing is the negative 2. We're going to have to tweak our integral with the negative 2 to the right of the integral sign, and we can't just do that willy-nilly. We have to balance it out front with negative 1/2. So negative 2y dy becomes our du. And out here we have our negative 1/2. All right, we're ready to integrate. Let's simplify first to the left of the integral sign. Negative 1/2 times 2 pi is negative pi. And we are integrating. What is the antiderivative of e to the u? Well, e to the u is its own derivative. It's its own integral. So the antiderivative is itself e to the u. And let's plug back in our u sub, negative y squared. And we will evaluate from 0 to 1. Okay. Let us evaluate. Plug in the 1. Our negative pi is still out front. E, and our power is y squared negative, so 1 squared is 1, and that negative makes it negative 1, so we get e to the negative first, or 1 over e. And then we subtract, plug in our lower limit. 0 squared is 0, e to the 0, or anything to the 0 is 1. So here is the exact answer, and if we plug that into our calculator, we can get the approximate answer of 1.986. Units cubed, again, because we're finding some volume. And we got a note down here. Let's see what the note is. Okay. So to see the advantage of using the shell method in this example, solve the equation x equals e to the negative y squared for y. Well, if we want to get that y alone, we're going to have to do log both sides, do some other stuff, and we wind up with this piecewise function. Y is equal to 1 for all x values between 0 and e to the negative 1 power. And from e to the negative 1 to 1, our value is the square root of the negative ln of x. So we would then use this equation in the disk method, which would be much more complicated than what we just did. Sometimes that shell method is preferable. So let's compare the disks and the shell methods. And let me just make this here a little bit bigger. So the disk and the shell methods can be distinguished as follows. For the disk method, the representative rectangle is always perpendicular to the axis of revolution. Whereas for this new shell method, the representative rectangle is always parallel to the axis of revolution. So the first two pictures here are the disk method. If we have a vertical axis of revolution, it is pi, the integral from c to d, capital R squared minus lowercase r squared, dy. We are parallel or perpendicular to our axis of revolution. If we have a horizontal axis of revolution, we are still perpendicular to it. But now we are integrating with respect to x. Our width of our rectangle is delta x, so we have dx in our equation. And it's pi integrated from a to b of capital R squared minus lowercase r squared. Upper radius minus lower radius each squared. And then we compare this to the new shell method. So for the shell method, vertical axis of revolution, we are parallel to our axis of revolution now. So our formula is 2 pi integrated from a to b of p of x times h of x dx. For a horizontal axis of revolution, here it's the x-axis, we are parallel with our representative rectangle, so our integral is 2 pi integrated from c to d of p of y times h of y dy, integrated with respect to y.